A volcanic island is one of the most unstable places you could ever choose to build. Yet ancient civilizations did much more than just build there. They mastered these treacherous landscapes using two silent partners, geometry and gravity. By the end of this video, you will understand the precise methods that allowed them to defy nature's chaos and create structures that have stood for thousands of years. How did they calculate perfect angles without modern tools? What secret did they discover about using a stone's own weight to make it unshakable? The answers reveal a lost chapter in human ingenuity. What does it truly mean to build something that lasts? A newly formed volcanic island is a landscape of pure chaos. It is a world of steep, unstable slopes and rock so fresh it is still settling. The ground beneath your feet is not solid earth but a loose, porous crust, constantly shifting with every tremor. Rain and wind carve deep gullies in hours, and the entire mountainside can slide into the sea without warning. For any builder, this is the ultimate nightmare. Traditional methods were useless here. A standard stone wall built on flat, stable ground would be shattered by its first earthquake. A foundation dug into this loose rubble would simply sink or slide away. These pioneers were not just building structures, they were solving a puzzle written in fire and stone, forced to invent an entirely new way of thinking about stability. To understand the sheer genius of their solutions, you must first feel the immense weight of the problems they faced. The solution began with a single, deliberate line scratched into the raw volcanic rock. Picture an ancient builder standing on that treacherous slope, ignoring the chaos to focus on a simple, powerful truth. A perfectly symmetrical foundation could tame the unstable earth. This was geometry's first and most vital principle in their fight against nature. They realized that a symmetrical base, whether a square, a rectangle, or a circle, distributed the immense weight of a structure evenly in all directions. On ground that shifted unpredictably, this even distribution was everything. It prevented one corner from sinking faster than another, stopping the fatal lean that would topple any ordinary wall. But how did they achieve such precision without modern instruments? Their tools were elegantly simple: a length of rope, some wooden stakes, and a fundamental understanding of triangles. They knew that a triangle with sides in the correct proportion would always form a perfect right angle. By using a knotted rope as a giant measuring tape, they could lay out the corners of a platform with astonishing accuracy. This was not written geometry from a textbook. It was mathematics born from direct observation and generations of practiced skill. They watched, they built, they learned what worked through trial and error. The proof was in the platform itself, a level, stable stage where none should exist. This careful alignment was the silent promise that the stones to follow would not tilt or slide into the sea. That first symmetrical outline was more than just a building's footprint. It was a declaration of order over chaos, the essential first step in making the mountain itself a willing partner in their ambitious constructions. With the geometry of the platform established, the builders faced their next great challenge. How could they make the structure itself resist the island's constant shaking and howling winds? Their answer lay in a force that was always present, the unseen hand of gravity. They learned to use the immense weight of the stones not as a burden, but as the very source of their stability. This was a brilliant inversion of the problem. Instead of fighting the forces of nature, they invited one of its most powerful agents to join their side. A structure with a low center of mass and tremendous weight was incredibly difficult to tip over. Think of a wide, heavy-bottomed toy that a child cannot knock down. The builders applied this same principle on a monumental scale. They intentionally designed their walls and platforms to be heaviest at the base, creating a deep, unshakable anchor into the unstable ground. This was achieved through simple yet profound design choices. Walls were built significantly wider at the bottom and then carefully tapered as they rose higher. Each massive stone block, carefully fitted into this sloping wall, pushed its weight downward and inward, locking the entire structure together. The collective mass of the stones created a form of inertia, making the building want to stay exactly where it was. When an earthquake struck, this heavy, balanced form would sway with the earth rather than fracture against it. The wind, no matter how fierce, would find no purchase on a form that was rooted by its own immense weight. This was not written in a formal law of physics, but it was a law they had discovered through observation and feel. They understood that by giving their buildings a deep, heavy center, they could make gravity itself the guardian of their work, a silent, constant force holding their creations firm against the chaos. Far out in the vast Pacific Ocean, on the remote shores of Rapa Nui, the silent Moai stand as eternal proof of this ancient mastery. These towering figures are not simply placed on the ground. They are anchored to the island by massive stone platforms known as ahu. To the untrained eye, an ahu might look like a simple stone wall or a basic foundation. But it is a masterpiece of engineering, a sophisticated structure designed specifically to conquer the island's unstable volcanic soil. The builders of Rapa Nui understood that the ground beneath them was a deceptive and shifting partner. Their response was to create a platform so precisely engineered that it would become one with the earth itself. This began with an obsession with geometric perfection. Before a single statue was raised, the builders leveled the ground with painstaking care. They used water-filled trenches to find a true horizontal plane, ensuring the massive platform would not tilt over time. Then they aligned the ahu itself with celestial markers, often positioning its long, straight face to parallel the path of the sun or specific stars. This celestial alignment was not just for ceremony. It provided a fixed, unchanging reference line from the cosmos, a permanent guide for ensuring the platform's walls were perfectly straight and its corners true. This geometric precision created a perfectly balanced stage, a stable distributor of weight that could handle the immense load to come, and that load was almost unimaginable. The ahu platforms were constructed from thousands of tons of carefully fitted basalt stone. Upon this incredibly heavy base, they then placed the moai, statues weighing many tons themselves. This was the final, brilliant step. The combined weight of the platform and the statue created a gravitational anchor of phenomenal power. It pressed down on the loose volcanic soil, compressing it into a denser, more stable foundation. The entire structure, from the deep base of the ahu to the head of the moai, acted as a single, unified mass, its center of gravity kept low and wide. When storms battered the coast or tremors shook the ground, this immense weight and perfect balance allowed the ahu to absorb the energy and simply hold firm. It did not fight the island's instability. It used its own tremendous mass to become an inseparable part of the island. The ahu of Rapa Nui are more than just stone bases. They are the ultimate testament to a lost science, a perfect fusion of geometric planning and gravitational anchoring that has kept these stone giants watching over their land for centuries. But the stability of these massive platforms relied on something more subtle than sheer weight. It came down to the art of the wall itself, a technique known as dry stone walling. Without a single drop of mortar to glue them together, builders carefully selected and shaped each volcanic rock to fit its neighbor with astonishing precision. This was not a simple pile of stones. It was a three-dimensional jigsaw puzzle where every piece was locked into place by its own unique geometry and the constant downward pull of gravity. The genius of this method was its flexibility. On an island constantly vibrating with seismic energy, a rigid wall made of mortar would be brittle. It would crack and shatter under the strain. But a dry stone wall was alive. When an earthquake struck, the entire structure could shift and sway, the stones grating against each other as they settled into a new, still stable arrangement. The energy of the tremor was dissipated through countless tiny movements across the wall's face, rather than concentrating into a single, catastrophic fracture. Achieving this required immense skill. A master builder had to see the potential in every rough volcanic rock. They would turn a stone over in their hands, assessing its natural shape, looking for the flat face that would bear the load and the irregular bumps that would lock it firmly against the stones beside and below it. Each choice was critical. A perfectly fitted stone transferred its weight and the weight of all the stones above it down through the wall and into the foundation, weaving a web of interlocking stress that made the entire structure stronger than the sum of its parts. This ancient craft demonstrates a profound, almost intuitive understanding of physics. It shows how the careful consideration of shape and weight can create incredible resilience from the most chaotic of materials, a principle that echoes through all the great building traditions of the volcanic Pacific. This same principle of using geometry and gravity to create stability was applied on a breathtaking scale, reshaping entire mountainsides. A steep volcanic slope is a landscape in constant motion, where rainwater carves deep channels and loose soil slides downward with every heavy rain. The solution was to cut the mountain into a giant staircase by carving a series of level platforms or terraces into the hillside and supporting each one with a strong retaining wall. These builders transformed a dangerous, erosive slope into a stable, productive farm. Each terrace was a geometric intervention, a flat plane imposed upon a steep angle. The retaining walls were the key. They were not simple barriers, they were carefully engineered structures built with a slight inward angle. This batter, as it is called, used gravity to lock the stones of the wall more tightly together, pushing their collective weight back into the hillside they were holding. The flat terrace behind the wall became a trap for fertile soil and precious rainwater. Instead of washing all the nutrients down the mountain, water would soak slowly into the deep soil of each level platform, nourishing crops and preventing erosion. On a macro scale, this network of terraces fundamentally changed the hydrology of the slope. A single, uninterrupted hillside acts like a slide for water, gathering speed and destructive power as it flows downward. But a terraced slope breaks that flow into a series of gentle steps. Water is slowed, absorbed, and managed at every level. This massively reduced the risk of catastrophic landslides that could bury entire villages lower on the mountain. The terraced landscape became a unified system, a testament to how human ingenuity could partner with gravity and geometry, not just to build a single structure, but to tame an entire volatile environment for generations. This spiritual dimension reveals a deeper layer to the builder's geometric precision. For them, aligning a structure with the sun or stars was not merely a technical feat. It was a sacred act, a way of weaving their creation into the very fabric of the cosmos. They operated on a principle we now call sacred geometry, the belief that certain shapes, ratios, and alignments held profound spiritual power. A perfect square was not just a stable base, it was a symbol of the earth. A circle represented the eternal cycle of the heavens. By incorporating these forms and orienting their temples to the solstice sun, they were building a bridge between the human world and the divine order. This spiritual pursuit had a remarkable and perhaps unintended consequence. it often resulted in structures of unparalleled stability. The same perfect angles that held spiritual meaning were frequently the most efficient for distributing weight. A wall aligned to a cardinal point, for instance, often presented its strongest face to the prevailing winds, while the precise ratios used to please the gods also created a perfectly balanced and resilient form. Consider a temple gateway built to frame the rising sun on the summer solstice. To achieve this, its builders had to calculate the exact angle of the sun's path with incredible accuracy. This required a deep, observational understanding of astronomy, and the resulting gateway, perfectly oriented, would be inherently strong. Its walls were not arbitrarily placed, they were set along lines of cosmic significance that also happened to be lines of great structural integrity. The spiritual intent to harmonize with the universe forced a level of precision that mere practical construction might not have demanded. This fusion of faith and physics created monuments that were spiritually resonant and physically eternal. The stones were not just stacked, they were consecrated by alignment, their stability a testament to a world where science and spirit were one and the same. While the terraces mastered the flow of water across the surface, another, more intricate system was working just beneath. Across these volcanic islands, the most ambitious builders engineered networks of stone channels and reservoirs, carving a circulatory system directly into the mountainside. This was water management elevated to a high science, a direct application of geometry to command one of nature's most chaotic and destructive forces. Without precise control, water was the enemy. A single storm could send torrents rushing down a slope, carving deep gullies and washing away the soil that anchored entire platforms and temples. The solution was to calculate the perfect, gentle slope for every channel. Too steep, and the water would gain destructive speed, scouring the channel walls and eroding the ground below. Too flat, and the water would stagnate or overflow, seeping into foundations and weakening them from within. The builders used their simple tools, ropes and stakes, to lay out these channels with a consistent, shallow grade, a geometric line that coaxed the water along a predetermined path, turning a potential destroyer into a guided resource. And the power behind this entire system was the relentless, silent pull of gravity. From highland springs to the lowest settlements, water flowed effortlessly downhill, directed by these carefully laid stone conduits. It was a brilliant partnership, using geometry to design the path and gravity to provide the motion. This was not merely about survival or irrigation. It was a defensive strategy for their architecture. By giving rainwater a clear, controlled route to follow, they prevented it from taking destructive shortcuts through their walls and under their foundations. They were not just building structures, they were building an environment, a managed landscape where every element, even the flow of water, was directed by human calculation to ensure that their creations would endure for ages. The same mind that could navigate an empty ocean by the stars understood how to anchor a temple to a trembling island. For the Polynesian voyagers, the greatest mystery was not the destination, but the journey itself. They crossed thousands of miles of open water in double-hulled canoes, navigating by a deep, intuitive reading of the natural world. They mapped the sky, memorizing the precise rising and setting points of stars to create a celestial compass. They felt the subtle pull of ocean swells, understanding how currents curved around unseen islands dozens of miles away. This was a life lived in constant conversation with geometry and physics. The angle of a star above the horizon gave them their latitude. The curve of a wave told a story of distant land. Their survival depended on an intimate knowledge of angles, curves, and directional forces. When their canoes finally sighted the rugged silhouette of a new volcanic island, this knowledge did not get packed away. it became their most vital tool for building a new home. They stepped onto those unstable shores, already seeing the landscape through a navigator's eyes. The slope of a mountain was not just a steep hill, it was a current of earth flowing downward. Their task was to chart a stable course across it. The principles were directly transferable, just as they plotted a course by balancing the pull of a current against the push of the wind. They would lay out a village by balancing the pull of gravity against the push of the slope. The precise right angles they used to align their celestial compass were the same perfect angles they scratched into the volcanic rock to create a stable foundation. Their understanding was a portable system, a genius for reading patterns in nature that worked as well on land as it did at sea. This profound link reveals a culture for whom geometry was not an abstract science but a lived reality. Their architectural mastery on land was born from their survival skills on the ocean, a seamless translation of knowledge that turned the chaos of a new volcanic world into a place of enduring order. Deep within the island's quarries, another layer of this ancient genius was at work. The builders were not just moving rock, they were conducting a masterclass in material science. They knew that not all volcanic stone was the same, and their choices were deliberate, calculated decisions based on the unique properties of each type. Basalt, dense and incredibly strong, was the backbone of their most critical structures. This was the stone they sought for foundations and the massive blocks of load-bearing walls, where its immense weight and resistance to crushing force made it the perfect anchor against gravity's constant pull. In contrast, a lighter, more porous stone like volcanic tuff was often chosen for upper sections or for the intricate carving of statues. Its relative ease of shaping allowed for detailed work, and its lighter weight placed less stress on the structure beneath it. This intelligent selection was a physical calculation, a way of managing the building's overall weight distribution and ensuring its center of gravity remained low and stable. But finding the right stone was only the first step. The true artistry began with the shaping. Using harder stone tools, they would carefully fracture a massive basalt boulder along its natural crystalline lines. The goal was not to create a simple cube but a complex geometric form. Each block was painstakingly shaped to have multiple flat faces and subtle, interlocking angles. A builder would hold one stone against another, chipping away until the fit was so tight that a knife's edge could not slip between them. This precise geometry transformed a pile of individual rocks into a single, cohesive mass. The interlocking shapes prevented sliding, while the vast surface area of contact between stones distributed weight far more efficiently than a simple stack ever could. The process was a dialogue between the material and the maker. They learned to read the rock, understanding how its density, grain, and porosity would respond to their tools and perform under the immense pressure of a towering wall. This was the final, crucial piece of the puzzle, a testament to a culture that saw the potential for eternal stability hidden within the raw, chaotic heart of the volcano itself. A simple dirt ramp becomes a tool of immense power when you understand its geometry. To move a stone block weighing many tons up the steep side of a volcano, the early builders constructed temporary roadways of earth and stone, transforming an impossible vertical lift into a manageable, gradual ascent. This was the principle of the inclined plane, one of humanity's oldest and most brilliant simple machines. Its magic lies in trading distance for effort. Instead of fighting gravity directly to hoist a stone straight up, they used the ramp's long, gentle slope to coax the block upward, letting its own weight work with them, not against them. The entire success of this operation hinged on one critical calculation: the angle of the ramp. A slope that was too steep would demand more force than any team of workers could provide. making the task just as impossible as a direct lift. But a slope that was too shallow, while easier to pull against, would require an absurdly long ramp, a construction project in itself that consumed vast resources and time. The builders had to find the perfect middle ground, a geometric sweet spot that balanced human effort with practical logistics. They achieved this through generations of hard-won experience, learning to judge the exact incline that made a multi-ton block movable. Teams of workers, likely using ropes and rollers, could then slowly, steadily drag these colossal stones up the engineered slope. This temporary geometric feature was the key to everything that followed. It was the only way to deliver the massive foundation stones and towering statues to their intended sites, high on the unstable slopes. Without the ramp, the stones would have remained forever at the base of the mountain. With it, they could be precisely positioned to create the permanent gravitational stability that would defy the centuries. The ramp itself was a fleeting creation, dismantled or washed away by time, but it was the essential, temporary partner that made every lasting monument possible. A low rumble begins deep within the earth, a tremor that travels up through the soil and into the very stones of a village. For a moment, the world itself seems to shudder. In such a place, this is not a rare catastrophe but a regular occurrence, a force of nature the builders had to anticipate with every wall they raised. Their greatest innovation was not to build rigid, unyielding fortresses, but to create structures that could dance with the earthquake. They designed buildings that swayed but did not fall, that flexed but did not fracture. This was resilience engineered into the very shape of the architecture. Look closely at the ruins of these ancient sites, and you will see a recurring pattern. Doorways and windows are often trapezoidal, wider at the base and narrower at the top. This is not merely an aesthetic choice. It is a brilliant geometric solution to a deadly problem. The trapezoid is a fundamentally stable shape. Its sloping sides direct the immense forces of a tremor downward, channeling that energy into the strong foundation below, rather than letting it concentrate at the top where it could collapse the entire opening. It is a shape that guides chaos into order, the same principle applied to the walls themselves. Builders would sometimes incorporate flexible joints or layers of smaller, rounded stones between larger blocks. These acted as shock absorbers, allowing sections of the wall to shift and settle independently during a quake. The entire structure would move as a unified, yet slightly fluid, mass. Imagine a tall tree in a strong wind. Its trunk and branches bend. They do not resist until they snap. These ancient buildings were designed with the same philosophy, using geometry to grant them a kind of life, an ability to move and then return to rest. How did they learn which designs would survive? They learned from the failures. When a wall with square doorways collapsed and one with trapezoidal openings remained standing, the lesson was written in the rubble. This was a slow, meticulous process of iteration, a form of natural selection applied to architecture. The most stable shapes, the most forgiving angles, were the ones that were repeated and refined over generations. This proactive approach reveals a profound truth. These builders were not just reacting to their environment, they were negotiating with it. They understood that you cannot stop the earth from moving, but you can design a building that knows how to move with it. They used geometry as a language to speak with gravity itself, creating a dialogue between stone and tremor that allowed their work to endure long after the shaking had stopped. The silent, cobbled streets of Akrotiri tell a story of a civilization that did not just survive a volcano, but mastered it. Buried for millennia under volcanic ash on the island of Terrace, this Minoan town is a stunning example of urban planning in the face of constant geological threat. Here, builders did not construct isolated, sturdy buildings. They engineered an entire city to be resilient, a unified system designed to flex and breathe with the unstable earth. Wide, straight streets cut through the town, not just for grand processions, but as vital fire breaks and clear pathways for evacuation or aid if the earth shook. Every element of this urban blueprint was a calculated response to the environment. The very orientation of the buildings was a lesson in geometric foresight. Structures were carefully aligned to account for the region's dominant wind patterns, their long walls often positioned to present a streamlined face to the powerful gusts, reducing the wind's ability to push against them. This alignment also considered known seismic zones, avoiding the most dangerous fracture lines in the Earth's crust. The town layout itself was a form of macrogeometry, a network of interlocking blocks and open plazas that distributed the city's weight and population, preventing dangerous concentrations of stress on the landscape. The genius of Akrotiri extended vertically from the ground up. Builders employed a brilliant strategy of material balance. The lower floors of their multi-story homes were built with massive, robust stones, creating a deep and heavy foundation that anchored the entire structure. But as the buildings rose, the construction materials became progressively lighter. Upper floors often used wooden frames filled with a lightweight mixture of rubble and clay. This created a building with a low center of gravity and a lighter top, a configuration incredibly resistant to toppling. During an earthquake, the heavy base wanted to stay put, while the more flexible, lighter upper stories could sway without generating catastrophic force. This was urban stability engineered on a city-wide scale. Akrotiri was more than a collection of houses. It was a single, living organism designed for life on the edge, a complete blueprint for thriving in one of the most volatile places on Earth. The stones themselves were a language. In cultures shaped by volcanic mountains, the most sacred architectural form often mirrored the silhouette of the peak that dominated their world. A temple was not just a building, it was a symbolic mountain, a man-made conduit between the earthly realm and the heavens. This deep cultural belief directly shaped the geometry of their structures, leading to designs that were spiritually profound and remarkably stable. The pyramid is the ultimate example of this fusion. Its sloping sides were a representation of the sacred mountain, a stairway for the gods to descend and for human prayers to ascend. But this symbolic form is also one of the most resilient shapes ever conceived by builders. The wide, heavy base and the inward sloping faces create a center of gravity that is incredibly low and centered. This makes the pyramid exceptionally resistant to lateral forces, like the relentless push of the wind or the violent shaking of an earthquake. The slanted walls act like a series of ramps, directing the energy of a tremor downward and dissipating it into the massive foundation. A square tower of the same height would be far more likely to topple, but the pyramid, by its very geometry, is designed to shed force and stand firm. This was not a coincidence. The spiritual imperative to build a symbolic mountain demanded a form that was inherently, physically eternal. The meaning and the mechanics were two sides of the same stone. The same cultural belief that valued a connection to the divine also valued permanence, and this drove the selection of a shape that achieved both. Every block in such a structure carried a dual purpose. Its weight contributed to the gravitational anchor that held the temple fast, while its position in the overall form reinforced a story of creation, power, and cosmic order. The architecture became a physical prayer, its stability a testament to the truth of the beliefs it represented. The stones did not just tell a story of faith, their enduring arrangement guaranteed that the story would be heard for 1,000 years. A profound silence eventually fell over these once bustling building sites. The rhythmic sound of stone shaping stone faded away, and the quarries, ramps, and platforms were slowly reclaimed by jungle and volcanic ash. With the decline of these civilizations, something equally monumental vanished: the intricate knowledge of how to build in harmony with a treacherous Earth. The geometric rules and gravitational principles that were once common knowledge to every master builder did not disappear in a single moment. They eroded generation by generation, like a coastline worn down by the sea. In cultures that relied on oral tradition, the death of a single master without a fully trained apprentice could sever a critical link in the chain. The precise ratio for a stable ramp angle, the secret to selecting the perfect interlocking stone, the subtle inward tilt that made a wall earthquake-proof, these were not written in manuals. They were stored in memory, passed down through demonstration and practice. A catastrophic event could accelerate this loss dramatically. A volcanic eruption, a tsunami, or a period of intense warfare could scatter a population, breaking apart the tight-knit guilds of builders and leaving no one behind to continue the work. The knowledge became fragmented, then simplified, and finally it turned into legend. We are left today with the magnificent results of their labor, but we are still reverse engineering the methods. We can measure the angles and weigh the stones, but we cannot hear the conversations between the old master and the young apprentice standing before a newly laid foundation. We have lost the feel of the craft. This historical mystery forces us to wonder what other brilliant techniques have been completely forgotten. What sophisticated understanding of physics, expressed only through practical action, vanished when the last person who held it took their final breath? The silent stones hold their secrets tightly, reminding us that our current picture of their engineering genius is still incomplete, a puzzle with many pieces forever lost to time. A modern archaeologist stands before the same ancient platform, but their eyes are no longer limited to the weathered surface of the stone. They hold a laser scanner that paints the structure with millions of invisible data points, creating a perfect digital twin. This high-resolution 3D model reveals what centuries of erosion and the human eye have hidden: the breathtaking precision of the original build. Invisible slopes, subtle curves, and interlocking angles that seemed rough and irregular are now exposed as deliberate, calculated features. This technology allows us to virtually weigh each stone, calculating the exact center of mass for the entire structure. We can now see that the builders did not just build heavy, they built with a precise understanding of balance. Their platforms were not merely flat, they were engineered with a minuscule, intentional convex curve, a geometric feature that actively shed rainwater and strengthened the edges against erosion. Ground-penetrating radar sends pulses deep into the earth, mapping the hidden foundation. It reveals that the builders did not stop at surface level. They often dug down through layers of unstable volcanic rubble to reach a more solid substrate, then filled the trench with a specific mix of larger stones and compacted soil, creating a deep, rigid base that acted like the root of a tree. These technological glimpses confirm a startling truth: their geometric calculations were not approximations. The angles of their walls, the slopes of their ramps, and the distribution of weight were so precise that they rival what modern engineers might design with advanced software. They possessed an intuitive mastery of physics, a feel for how forces flow through stone and earth. We are now using the tools of the future to conduct a long-distance conversation with these ancient masters. Each laser scan and radar image is like receiving a message, a detailed set of instructions written not in words but in stone, showing us just how deliberately and intelligently they tamed a volatile world. These solutions echo far beyond the shores of Rapa Nui or Thera. From the vast Pacific to the Mediterranean's fiery rim, cultures who never met, who spoke entirely different languages, looked upon their unstable volcanic homes and arrived at nearly identical answers. It is a story of parallel invention on a global scale. The Maori of New Zealand, the inhabitants of the Canary Islands, the builders of ancient Crete, all faced the same fundamental problems of steep, eroding slopes and trembling ground. And remarkably, they all developed terracing. They all cut the mountain into geometric steps, using gravity to hold the soil and water in place. They all discovered that a wide, heavy base was the key to stability, leading to pyramidal structures and platforms that seemed to be siblings separated at birth. They all mastered dry stone masonry, fitting rocks together without mortar to create walls that could dance with earthquakes. This is not a coincidence. It is evidence of a universal problem-solving logic. When presented with the same brutal environmental pressures, the human mind, guided by observation and trial, tends to find the same elegant pathways to survival. The principles of geometry and gravity are not cultural inventions. They are fundamental truths about our physical world. A wide base is always more stable than a narrow one. A sloping wall will always direct force downward. A perfectly fitted stone will always transfer weight more efficiently. These are the immutable laws of physics, waiting in the stone itself to be discovered by anyone who looks closely enough. This global perspective shifts our appreciation from the genius of a single culture to the ingenuity of humanity itself. It suggests that our shared capacity to read the world, to see the patterns in chaos and the order in the raw forces of nature, is one of our most profound and unifying traits. The same silent partners, geometry and gravity, were available to every civilization standing on that unstable ground. The real wonder is how many of them, independently, chose to listen. A structure built on a volcano had to be a fortress against the sky itself. These islands were battered by seasonal hurricanes and drenched by rains that could turn dry gullies into raging rivers in minutes. In response, the builders sculpted their architecture into aerodynamic forms, using geometry to slice through the wind and shed water with the efficiency of a leaf. A rounded corner on a stone platform was not an aesthetic whim. It was a calculated defense, a curve that allowed hurricane-force winds to flow smoothly around the structure rather than slamming into a flat wall with enough force to topple it. The steep pitch of a thatched roof was another geometric calculation, an angle so severe that even the heaviest tropical downpour would be flung clear, preventing water from soaking through and rotting the supports or, worse, pooling and adding dangerous weight to the upper levels. Every slope and curve was a dialogue with the elements, a way of inviting the wind and water to pass by without causing harm. This mastery extended to creating comfort from chaos. Long before mechanical cooling, these builders engineered a passive climate control system by aligning their buildings with the prevailing winds. They positioned windows and doorways to create a funnel, channeling the steady ocean breeze directly through the living spaces. The entire structure became a wind-catching device, pulling cool, fresh air indoors and pushing stale, hot air out. This was not just about comfort, it was about preservation. A well-ventilated building resisted the insidious growth of mold and mildew that could weaken organic building materials over time. The placement of a village itself was a climatic calculation. Settlements were often situated on slopes just above the shoreline, high enough to avoid storm surges but perfectly positioned to catch the full benefit of the cooling trade winds. Their understanding was holistic. They saw the ground, the air, and the water as a single, interconnected system, and their geometry was the language they used to negotiate with all of it at once. They were not just building shelters, they were crafting micro-environments, designing entire habitats that could breathe with the wind, shed the rain, and remain steadfast anchors in a world of relentless natural force. The builder's hands were the final instrument of calculation, holding tools of elegant simplicity. A carved stone weight hung from a cord, a plumb bob, was their unwavering guide to the true vertical. In a world of shifting slopes, this tool gave them a single, constant reference line drawn directly by the force of gravity. When dangled, the weighted cord pointed unerringly toward the center of the Earth, defining a perfect perpendicular. Against this line, they could check the lean of a wall, ensuring its immense weight was being channeled straight down into the foundation. But a single vertical line was not enough to build a stable platform. For that, they needed perfect right angles, and their solution was a length of knotted rope. 3 knots, precisely spaced, could transform a simple cord into a powerful geometric calculator. By stretching the rope so that one section measured 3 units, another 4, and the longest 5, they forced it into the shape of a perfect right-angled triangle. This was the practical application of a principle we now call the Pythagorean theorem, though they knew it as a proven truth of the physical world. Once this triangle was established on the ground, they could extend its lines to mark out the square or rectangular footprint of a temple or an Ahu platform. This method was so reliable and so simple to teach that it democratized precision engineering. A master builder could lay out the critical angles himself, and then teams of workers, each armed with identical knotted ropes, could replicate that accuracy across the entire construction site, ensuring every wall met its neighbor at exactly 90 degrees. The true sophistication was never in the rope or the weighted stone. It was in the shared knowledge, the communal understanding of how to use gravity and simple geometry to impose a perfect, lasting order onto the raw, chaotic landscape. A perfect geometric design remained just a drawing in the sand without the human force to bring it to life. These monumental projects required a society organized like a single, complex machine. Moving a multi-ton stone block was not a task for a lone family or a small clan. It demanded the coordinated muscle of an entire community, a shared understanding that the stability of the temple was the stability of their entire world. This was a social contract written in stone. The work was divided with astonishing efficiency. Teams of quarriers selected for their strength and knowledge of the rock would work at the source. Transport crews skilled in the use of ropes and rollers would navigate the temporary ramps, and at the site itself, the master builders and their apprentices directed the final, precise placement of each block. This was not chaotic, back-breaking drudgery. It was a synchronized operation, likely accompanied by rhythmic chanting or drum beats, turning immense physical effort into a coordinated, almost ritualistic performance. The true longevity of their techniques, however, depended on a system far more fragile than any stone wall, the unbroken chain of knowledge passed from an experienced master to a watching apprentice. This was how the secrets of geometry and gravity survived. An old builder would not simply tell a young learner the perfect angle for a wall. He would place the knotted rope in the youth's hands, guide them to stretch it, and have them feel the truth of the right angle for themselves. The knowledge was transmitted through action and corrected through practice. An apprentice learned to select a stone not by a list of rules, but by holding one after another, their hands learning the difference between a rock that would settle and one that would shift. This ensured that the geometric principles were not abstract theories but living, breathing skills. The community's collective memory became the true library, storing the hard-won lessons of which designs had collapsed in the last quake and which had held firm. Every person, from the strongest laborer to the most precise stone shaper, understood their role in a project that would outlive them all. The enduring stability we marvel at today was built on this dual foundation, a deep understanding of physical law married to an unshakable social agreement that they would build together for the generations yet to come. A god did not build these walls, but the story says he taught the people how. In the flickering firelight of an elder's home, a legend is told of a deity who descended to show the first builders how to use the bones of the earth. It is a powerful metaphor, but it is also a precise technical manual in disguise. The bones of the earth are the dense, load-bearing basalt stone found deep in the quarries. The story encodes a vital truth that stability comes from using the strongest, deepest rock as the skeleton of any structure. These oral histories were not mere fantasy. They were the living libraries of their time, preserving complex engineering concepts in a form that was memorable, repeatable, and could survive for centuries. Another tale might speak of a hero who held up the sky, a seemingly impossible feat of strength. Yet this could be a poetic description of achieving perfect structural equilibrium, where the weight of a massive roof is channeled down through pillars and walls so efficiently that the entire building appears to hold up the heavens themselves. The language of myth was the language of physics, translated into human-scale drama. A chant about a great flood might not just describe a deluge of water, but the clever network of channels and reservoirs that managed it, turning a destructive force into a life-giving resource. The priorities of the builders are etched into these stories. The gods who feature most prominently are often those of earth and sky, the very forces their architecture was designed to negotiate with. By decoding the metaphors, we find unexpected clues. A story about a magical rope that could not be broken might refer to the unyielding strength of a perfectly laid foundation line. A legend about a warrior testing his strength against the wind could be a record of testing different architectural forms in a hurricane-prone bay. These narratives were a sophisticated memory technology, ensuring that the most critical lessons of geometry and gravity were not just known but remembered, sung, and passed down through the ages as a sacred trust. The stones tell one story, but the songs tell another, and only by listening to both can we begin to hear the full conversation between the builders and their volatile world. A collapsed wall tells a story the standing ones cannot. Scattered across these ancient sites are the ruins of platforms that sank into the soft soil and walls that fractured under their own weight. These were not hidden away. They stand as stark reminders, the critical lessons in a long education of trial and error. Each failure was a brutal but honest test of their principles. A platform that tilted and cracked revealed a miscalculation in its foundation's angle, a slope that directed weight sideways instead of straight down. A wall that toppled inward showed they had misjudged the batter, the inward lean that was supposed to lock the stones together. When a structure slid down a slope, it was a clear sign the builders had underestimated the need for a wider, heavier base to anchor it against gravity's relentless pull. These were not defeats to be forgotten. They were the data points that sharpened their genius. The master builders would have studied these collapses with a forensic eye, running their hands over the fractured stones to understand precisely how the forces had overwhelmed the design. The knowledge gained from a sunken platform on one side of the island would directly inform the deeper, more robust foundation for the next temple built on similar ground. A collapsed wall taught them the exact limits of a particular stone's strength or the perfect tightness for fitting blocks. This process of refinement was slow and often costly, but it was how their empirical science evolved. It moves them from mythical, infallible architects into something far more relatable, a community of brilliant problem solvers who learned more from their occasional stumbles than from their countless successes. Their entire engineering tradition was built, in part, upon a foundation of carefully analyzed ruins, proving that true stability is not born from perfection, but from the wisdom to understand why things fall. That profound sense of solidity you feel standing before these ancient platforms is not an accident of time. It is the direct result of a design philosophy where the most stable form was also the most beautiful. The builders were not choosing between strength and elegance. They were discovering that one was the natural consequence of the other. The clean, sweeping lines of a terraced hillside, the harmonious proportions of a pyramid, the gentle inward slope of a massive wall, these were not decorative afterthoughts. They were the geometric solutions that guaranteed survival, and in doing so, they created an aesthetic of profound stability that we still find deeply comforting. Why does a structure that looks unshakable also feel so right to our eyes? It is because our sense of beauty is often rooted in an intuitive understanding of balance and order. A building that appears perfectly poised, that seems to grow from the earth rather than perch upon it, resonates with our own desire for safety and permanence. The builders of these islands tapped into this universal truth. They found that a wall with a wide base and tapered top was not just resistant to earthquakes, it was visually grounded and powerful. A series of level terraces cut into a mountain was not just practical, it created a rhythm of horizontal lines that calmed the chaotic slope. The perfect right angles of a foundation did more than distribute weight, they gave the structure a clarity and a sense of intentional peace. This was an architecture where every curve had a purpose and every angle a physical reason for being. The beauty was not applied like a coat of paint, it was baked into the very physics of the construction. The most efficient way to manage gravity's pull and the Earth's tremors resulted in forms that we have revered for millennia. For these master builders, creating something that would last was the highest form of art, and their silent partners, geometry and gravity, were the ultimate muses. Getting these stones to the build site was a physics problem of epic proportions. A multi-ton block of basalt is not just heavy, it is a force of nature in itself, resisting movement with every fiber of its being. The challenge was not merely to drag it, but to outsmart its immense weight, to coax it across miles of rugged, uneven terrain. The theories on how they achieved this are as varied as the islands themselves, but they all share a common thread, a deep reliance on geometric foresight and a clever partnership with gravity. One of the most enduring images is that of log rollers. Teams of workers would lay a track of felled trees in front of a massive stone slab, which itself rested on a wooden sledge. With teams pulling on ropes, the sledge would inch forward, its weight borne by the rolling logs. This simple system transformed sliding friction into the far easier rolling friction. But its success hinged on a constant geometric calculation. The path had to be as level as possible, requiring builders to clear and sometimes even grade the land ahead of the transport crew. Any significant upward slope multiplied the force needed exponentially, while a downward slope risked the load running away out of control. It was a constant negotiation with the landscape's angles. Another compelling theory involves water. On certain terrains, they may have dug shallow, temporary canals, lining them with clay to hold water, and then floating the massive stones on rafts. A floating stone is a weightless stone, its burden temporarily suspended by buoyancy. This method would have turned a grueling land haul into a manageable waterway journey, using the fluid properties of water to negate gravity's grip. But even this required precise planning. The canal had to follow a consistent, gentle downhill slope, a geometric line calculated with ropes and stakes to ensure a steady, controlled flow. Too steep and the water would rush away, too flat and the raft would stall. How did they calculate the force needed? They learned it through collective muscle memory. Generations of workers knew the feel of a rope when a block began to move, the precise point where human effort and the stone's inertia reached a balance. They understood that a wider, more stable load was slower but safer, while a taller one was a tipping hazard. They were solving complex equations of force and momentum with their bodies, their experience, and their shared intuition. Solving the transport puzzle was the critical first act of stabilization. A stone perfectly shaped for a wall was useless if it remained in the quarry. By mastering the journey, they ensured that the right material arrived at the right place, ready to be locked into a structure designed to stand for 1,000 years. These ancient builders left us with more than just ruins. They left a new way of seeing the world. They stood before raw, untamed chaos and perceived a hidden order, a silent language written in the angles of stone and the constant pull of the earth. Their true legacy is this shift in perspective, a reminder that the most profound stability comes not from fighting nature's forces, but from understanding them. The principles they forged in fire and stone, the timeless ideas of symmetry, balance, and intelligent design, are not relics of a distant past. They are the bedrock of modern engineering, from the earthquake-resistant skyscrapers that sway with tremors to the carefully calculated slopes of a dam. This journey into their world invites you to look around with fresh eyes. Notice the geometry in the arch of a bridge, sense the gravitational anchor in a wide building foundation, and appreciate the brilliant calculations, both ancient and modern, that hold our world together. If these whispers from the past have sparked your curiosity, subscribe for more journeys into the depths of history. We would love to hear which of these incredible achievements resonated most with you, so share your thoughts in the comments below. The silent wisdom locked within these volcanic stones is now speaking directly to our modern world. We are rediscovering that the ancient principles of geometric balance and gravitational anchoring are not historical curiosities, but timeless truths for building resilience. In earthquake-prone regions like Japan and California, contemporary engineers are designing skyscrapers that do not rigidly resist tremors, but sway with them, a direct echo of the flexible dry stone walls that shifted and settled without collapsing. The wide, tapered bases of our most stable modern structures are geometric descendants of those ancient platforms, using a low center of gravity to defy lateral forces. We are even revisiting the concept of base isolation, where a building is essentially decoupled from the shaking ground, much like how a perfectly fitted stone in a wall could move independently before settling back into place. This is not mere imitation, it is a validation. It proves that these early builders discovered fundamental laws of physical stability through observation and feel, laws we are now formalizing with advanced physics and computer modeling. Their legacy, therefore, is far more than a collection of awe-inspiring ruins. It is a living knowledge, a profound reminder that the most elegant solutions often come from working in harmony with the immutable forces of our planet. The stones they left behind are not just monuments, they are mentors, and their lessons in enduring strength are as vital today as they were 1,000 years ago.